So this is the second time I've talked about catalysts. The first time was when I introduced it with transition metals, and there'll be a third time. If you go under the biofuels in the future, the biofuels video will come out, and I'll just be comparing the enzymes as organic catalysts versus inorganic catalysts. And so this one here is now kinetics, and so we're focusing a lot on the graphs. So that's the addition for this second time talking about catalysts, and the third time will be about inorganic versus organic. And so transition states are when we don't really know what these things are, we're just sort of guessing. So if there's like an A to a B, then we assume that they have to have contacted before they do something weird. So this would probably be a BC. So there's a BC molecule, and they're joining up in some weird way, and then when you get your products, there's an ABC. So I don't think anyone would argue that they must contact in some way, and we just don't know how, and it's just instantaneous. Whereas an intermediate we can actually collect. So it is quite possible that this ABC is actually a stable product, and then we can collect it. And then we can also just keep it reacting and get the A, B, and the C. Okay, so if it's a stable product, it's formed as a progression of the reaction. It's called the intermediate, whereas the transition states are these complexes that we're assuming that we never really know about. Okay, and just to jump the gun a little, the enzymes can lower that transition state by either causing pressure on the bond, as I said in the last video, or by actually just lining them up and holding them in place so that they can actually occur, or creation of the intermediates, because there might not be an intermediate. It might actually normally be like this, and the energy that needed to react is much, much higher than if there was an intermediate that was produced. And so if there was an intermediate produced, then we only have to go to this height here as well, okay, rather than go all the way up here. Okay, so I'll show that in the graphs because that's the point of this video. So just a review again. So a catalyst increases the rate of reaction without being used up in the reaction by lowering the activation energy by creating activated complexes or the creation of intermediates. So this graph's a little bit better in showing the more stable activated complex. And this one here is also a little bit better because you can imagine that it may take a lot of energy to get from A to B. And so if you've got A to C, and if you've got a B in there, that might be easier to go step by step rather than one huge jump. Okay? And so the real focus of this then, because that's sort of touched on several times, is just the Maxwell-Boltzmann curve. So if you're asked to explain one or draw one, just make sure that you put the activation energy with a catalyst lower, and then demonstrate that you've got all these extra particles now that can also react. Therefore, if there's a collision, there's a much, much higher number that will have the probability that will have enough activation energy to react. Okay, and the second thing is this graph here, which we've touched on many times already. If you're asked to redraw it, make sure you just draw it as a lower activation energy curve here if there's a catalyst there. Okay, so just really focus on all those different graphs as this is kinetics.